5,000 tons of steel, motionless on an incline, wheels groaning, engineers at a loss. Then, with a subtle pull of a concealed lever beneath the cab, a powerful surge from a hidden engine deep within jolted the colossal train back to life. For decades, American railroads relied on this discreet Franklin booster to overcome the one obstacle steam engines alone could not surmount: the immense power required to initiate movement from a complete standstill. But why did railroads discard this vital invention, effectively eradicating it almost overnight? To comprehend this, one must grasp the sheer difficulty of setting a stationary train in motion. 5,000 tons of steel, each ounce of it seemingly fused to the tracks by an invisible force: static friction. At rest, every bearing, every journal box, every steel-on-steel contact point is tightly locked. The primary wheels aren't merely contending with gravity or the train's mass. They're combating a type of unseen adhesive, static friction at the interface and within every axle. Theoretically, it demands 3 to 5 times more effort to initiate the rotation of those wheels than to sustain their motion once they're rolling. In practical scenarios, with frigid conditions, rigid grease, and a significant gradient, that disparity can amplify even further. A moving train tends to stay in motion. This is rolling friction, low and foreseeable. But when a train is stationary, static friction exerts its full resistance. It requires a tremendous burst of force to dislodge thousands of tons from their resting state. For every ton of cargo, rolling resistance at a crawl might be 4 or 5 pounds. However, to commence movement, one is looking at 12, 15, sometimes even more. Multiply that by a mile-long line of loaded cars, and the figures quickly become alarming. Locomotive cylinders are rated for thousands of horsepower, yet at 0 miles per hour, they are at their weakest. The pistons can exert strong pressure, but without speed, there's no momentum to aid. Worse, the drive rods can encounter what railroaders term dead center, where the pistons misalign, causing the entire apparatus to stall until gravity, or a stroke of luck, resolves the impediment. This is precisely why numerous steam trains needed an auxiliary engine to assist in departing the yard. It wasn't about the impending hill. It was about conquering inertia from the very first inch. Each time a heavily laden freight train idled on a gradient, crews and dispatchers bore the consequences. An auxiliary engine necessitated an additional crew, more coal, more water, and a 20-minute loss for coupling and brake testing. All this just to advance the train beyond the initial 100 feet. This was the inertia trap, where every pound of steel acted as an anchor, and the primary engine reached its maximum capacity before the journey even commenced. A stalled freight train on an incline didn't merely signify toil in the cab. It represented a significant operational headache for the entire railway system. When the main locomotive proved incapable of moving the load, the dispatcher had to resort to the most undesirable option in their arsenal: the helper engine. This entailed summoning another crew from their rest quarters, igniting a second boiler, and consuming more coal and water simply to relocate a train a few miles. By the 1930s, each helper assignment incurred approximately $2 additional per hour in wages for the engineer and fireman alone. Factoring in the cost of coal, sometimes a ton or two per push, and thousands of gallons of water, the expenditure escalated with every journey up the incline. However, the true difficulty wasn't solely in salaries or fuel consumption. Every instance a helper was required, the entire operation decelerated to a crawl. The train had to halt at the base of the gradient, await the pusher's descent, couple up, and conduct a comprehensive brake test. Only then could the double-headed consist laboriously ascend the hill. At the summit, the procedure reversed. Another stop, detach the helper, test the brakes, and wait while the pusher returned to its base station. On a fortunate day, This routine consumed 15 or 20 minutes per train. On a bustling line, with helpers constantly shuttling back and forth, these delays accumulated rapidly, eroding schedules, monopolizing main tracks, and leaving crews idle on sidings. For the accountants in management, the figures were unfavorable. Every helper movement implied increased wages, more coal, more water, and more lost time. Multiplying this by dozens of trains daily, the railway's operational costs expanded significantly. This is why any mechanism capable of extracting a few extra pounds of pulling power from the primary locomotive without requiring an auxiliary seemed like a miraculous solution. The prospect of an integrated device concealed beneath the cab that could transform dormancy into raw, tractive effort was sufficient to capture the attention of even the most skeptical superintendent. In the early 1920s, a small company based in Philadelphia focused on a persistent issue for every major railroad: moving a heavy train without the delays and expenses associated with a helper engine. That company was Franklin Railway Supply. Their engineers investigated the inert weight on the trailing trucks, the so-called lazy wheels beneath the cab that supported thousands of pounds but contributed nothing to actual propulsion. Franklin's proposition was straightforward. Why not make those wheels perform useful work? The solution materialized in a series of patents, US 1 to 6024 and 153,475, filed during a decade when railroads desperately sought any competitive edge. Franklin's design was not merely a conceptual sketch. By 1923, they were marketing a compact two-cylinder steam engine designed to be directly affixed to the trailing truck. It was a tightly integrated unit, encompassing a gear case, a pair of pistons, and a clutch mechanism, all compressed between the intense heat of the firebox above and the grime of the ballast below. The company promised railroads a revolution: eliminate helper engines, save time, reduce payroll, and keep the main line operational. Their advertisements claimed this small engine could convert inert weight into an additional 15,000 pounds of pulling power at the rail. This was enough to initiate movement in a stalled freight train, where previously an entire second locomotive would have been required. Franklin's brochures and trade journal advertisements from the mid-1920s heavily emphasized numerical benefits. They promised fuel economy, expedited schedules, and the capability to move longer trains over existing tracks. The booster, they asserted, was the missing element that optimized the utility of every pound of a locomotive. The sales pitch proved effective. By the end of the decade, Franklin boosters were being installed on new engines across the nation, particularly on lines with steep gradients or heavy coal traffic. For railroad superintendents and financial personnel, it appeared to be a means of extracting greater profit from each run. However, the true test didn't occur in boardrooms or patent offices. It happened in the roundhouse, where the foreman, weathered, weary, and covered in grease, first encountered Franklin's secret engine. For the individuals responsible for maintaining locomotives, it represented another machine to service, another source of leaks to address, another reason to crouch beneath a hot firebox in the middle of the night. The promise was grand, but the work was arduous. And it was here that the booster's narrative transitioned from gauzy advertisements to harsh reality. The sole location on a steam locomotive where an additional engine could be concealed was the trailing truck, directly beneath the cab. These wheels were not intended to propel the train. They merely supported the firebox and prevented the locomotive's rear from sagging. However, Franklin's engineers recognized the potential in all that dead weight. With up to 40,000 pounds bearing down, those wheels gripped the rails, doing little more than simply rolling along. If that adhesive weight could be harnessed, it would provide a secret weapon for traction, especially when the main driving wheels began to slip. Instead of mounting the booster at the front or on the main drivers, they positioned it low between the rails, bolted to a cast steel bed plate on the trailing truck. It was an incredibly harsh environment. Above, the firebox radiated intense heat. Below, every mile brought a barrage of cinders, grit, and mud. The booster had to withstand it all, with steam pipes that flexed as the truck articulated over uneven track. Franklin's brochures presented neat diagrams depicting a compact assembly of gears and pistons shielded by robust castings. In reality, the unit attracted oil, water, and every pebble the ballast could propel. Mechanics referred to it as a grease pit. The gear case, positioned mere inches from the tires, was filled with oil to preserve the reduction gears. It remained sealed until the seals deteriorated, allowing dirt to contaminate the oil and transform into an abrasive paste capable of grinding steel to fragments within months. The booster operated akin to a car starter motor. Actuating a lever in the cab caused a gear inside the booster to slide, engaging with the axle. Instantly, those trailing wheels activated, propelling the train forward with a surge of torque. However, it could not remain engaged for extended periods. Designed for immense force at low speeds, the booster was concealed and robust, and its placement was crucial if it could be kept operational amidst the grime. A Franklin booster remained sealed within a cast-iron casing beneath the cab, yet its activation always originated within the cab itself. The engineer's hand would reach down, sometimes nearly to the floor, and pull a small latch or manipulate a stubby valve. This simple action sent a burst of compressed air rushing through a pipe to a cylinder mounted directly on the booster gear case. Inside, a heavy yoke propelled a steel idler gear sideways, out of its resting position, and directly into the teeth of the bull gear on the trailing axle. It resembled the mechanism of a car's starter motor, one gear sliding into mesh with another, designed to engage only when the speeds precisely matched. If the wheels were completely stationary or barely creeping, the teeth would mesh with a satisfying thunk. Immediately, the booster's own steam valves snapped open, admitting live steam from the main boiler into two small cylinders within the housing. With the valves open, the booster's pistons fired rapidly, rotating a crankshaft submerged in oil. That drive shaft propelled the idler gear, now firmly engaged with the trailing axle, unleashing a surge of raw, low-speed power directly to the rails via wheels typically reserved for passive rotation. The engineer observed no dramatic shifts on the gauges, only a novel auditory cue, a rapid, rhythmic chug, chug, chug from beneath the cab, distinctly different from the deep exhalation of the primary cylinders. The entire locomotive vibrated as the trailing truck abruptly transformed into a driving mechanism, aiding in dislodging the train from the grip of static friction. The brilliance of this apparatus lay in its elegant simplicity. No intricate linkages, no deferral for an additional engine to couple. The booster was poised for action, concealed yet perpetually ready. Akin to a car's starter, its design was for fleeting bursts of operation. Engage it at minimal velocity to initiate train movement, then disengage it before the gears attained excessive rotational speed. Upon completion of its task, the same pneumatic cylinder would retract the idler gear, allowing the trailing truck to revert to its customary passive state. For a brief interlude, inert mass became dynamic force, activated by a mere lever flick and a rush of steam. A Franklin booster was more than just a clever contrivance. It was a potent, unrefined solution tucked beneath the cab, awaiting its moment. On paper, the figures seemed almost implausible. With a simple lever activation, the booster imparted an additional 15,000 pounds of tractive effort directly to the rails. A substantial gain, not a trivial rounding error. This represented the critical difference between a train immobilized on an incline and one laboriously ascending a gradient. In terms of brute force, the booster's two compact cylinders could generate between 300 and 400 horsepower, albeit only at a crawling pace and solely for the duration of its engagement. There was a key limitation, however. The booster's design was singular. to overcome a train's static inertia from a standstill, or to maintain momentum when the primary driving wheels lost traction. It was never intended for continuous operation. Most engineers relied on it for just a couple of minutes, sufficient to get the heavy tonnage rolling, or to power through the most challenging portion of a short grade. Prolonged use incurred a swift and substantial steam consumption penalty. The boiler possessed finite capacity to supply multiple demanding cylinders simultaneously, and the booster earned a reputation as a prodigious steam scavenger. Excessive operation would visibly diminish the main pressure gauge, resulting in an exhausted fireman and a struggling locomotive. Yet, the absolute limit was speed. The booster's gearing was calibrated for walking pace. The moment the train surpassed 15 miles per hour, and certainly by 20 miles per hour, the auxiliary engine absolutely had to be withdrawn from service. Forgetting to disengage it and allowing it to accelerate while still engaged would subject its gears to enormous stress. While some boosters incorporated a centrifugal governor, an automatic mechanism that disengaged the gear as axle speed increased, not all did, and not every governor functioned reliably. Many a roundhouse received calls about a booster that had been used for too long, reporting stripped teeth, fractured housings, and occasionally a pile of shattered components where a perfectly functional idler gear once resided. As a foreman, I invariably instructed my crews, treat that booster like an automobile starter. Get moving, then disengage it promptly. If you push it beyond the safety margin, you'll be tidying up the debris. Below, in the maintenance pit, the allure of additional horsepower quickly evaporated. The booster's gear casing sat mere inches above the ballast, absorbing every particle of grit, cinders, and winter slush the tracks could offer. Oil seals had no chance of lasting. Within a week, the gear lubricant degenerated into a half-oil, half-abrasive paste, capable of transforming brand-new teeth into scrap metal before the subsequent inspection. Flexible steam joints, engineered to flex and sway with the truck, became persistent sources of leakage. Hot steam hissed out into the darkness, coating everything with a greasy film and transforming the workspace into a treacherous ice rink. Each time the engine entered the facility, a fresh puddle would appear beneath the firebox, and a new trail of oil would streak down the frame. The booster didn't just leak, it bled. Maintaining its functionality entailed contorting oneself beneath a scorching firebox, wrestling with frozen bolts, and extracting failed gaskets with numb fingers. Mechanics resented every minute spent in that position, particularly when a seemingly hour-long task ballooned into an all-night ordeal. The booster's reputation as a steam hog was well-deserved. Prolonged usage would cause the main boiler pressure to dip, forcing firemen into a frantic effort to maintain it. The roundhouse foreman concisely summarized the situation. Engineers adored them because they offered salvation on inclines. We loathed them because we had to crawl through the grime to repair them. Electric traction motors revolutionized everything. The inaugural generation of diesel-electric locomotives from EMD and Alco emerged with an inherent advantage that steam could never rival: full torque at zero speed. Unlike a steam engine, which struggled to overcome inertia, a diesel's traction motors delivered maximum pulling power the instant the throttle was advanced. There was no requirement for an ingenious clutch, no concealed steam lines, and no oil bath relentlessly grinding beneath the cab. The torque curve on an EMD-F unit remained constant from a complete standstill until the point of adhesion loss. No booster could contend with such performance. Railroad mechanical bulletins from the late 1940s and early 1950s began to convey a clear directive. As steam locomotives arrived for overhaul, repair shops were instructed to remove any components that proved more problematic than beneficial. Boosters were at the top of this list. Some were simply disconnected, their steam lines sealed, and gears left inactive. Others were completely excised, leaving behind empty castings or only the trailing truck as a silent testament to a bygone era. The reasoning was straightforward. With diesels handling all heavy starts, no one desired to waste hours repairing a device that had served its purpose. By the time steam locomotives were in their final stages of operation, one could walk through a roundhouse and discern the transformation. Where a secret engine once resided beneath the cab, now only a hollow shell remained. Another vestige of the steam era left behind by progress. Steam's old remedies disappear, yet the underlying challenges endure. Each advancement in efficiency carries unnoticed compromises. Modern locomotives require no concealed boosters, but engineers continue to grapple with the limitations of physics and the expense of intricacy. Progress buries its secrets, but nothing truly vanishes. It merely awaits a new predicament to bring it back into relevance. What will be the next subtle fix we inadvertently overlook?